Page number 53 of notes. Electric field electric field of two positively charged parallel plates of two positively charged parallel plates. Electric field of two positively charged parallel plates. Two positively charged parallel plates. Anusha, is the video clear to you?
Yes, sir. Why?
Okay, okay. Actually, there is some connectivity problem here. That's why I'm asking.
Video and audio both are clear.
Okay. Electric field of two positively charged parallel plates. So now we are drawing two positively charged parallel plates, two positively charged plates which are parallel to each other. So these are the two parallel plates, and both these plates are positively charged. So plus, 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 positive, positive. So there are three areas. One area is onto the left of this plate, one area is between these two plates, and one area will be onto the right of this plate. So we are dividing the entire area into three regions: region first, region second, and region third. So this is region first, this is region first, this is region second, and this is region third. So there are three regions. We have divided the total area into three parts. So sheet 1, this is our sheet 1, this is sheet 1, this is sheet 2, sheet 1, sheet 2, and because I am talking about a surface, so surface charge density of this sheet is sigma 1 and surface charge density of this sheet is sigma 2. So I have considered the surface charge density of this sheet to be sigma 1 and of this sheet to be sigma 2, sigma 1 and sigma 2. Now electric field in this region electric field due to this sheet, electric field, we know that the electric field always moves away from the positive charge and the electric lines of force comes inside the negative charge. So I have two positively charged plates. So because of this plate electric field will be in this area, because of this plate electric field, because consider that this is a parallel plane sheet of charge. So I have not drawn it like this, I have drawn it like this. Okay, so the positive charge will emit electric line of force here also, and positive charge plates will emit electric line of force here also. So this plate will emit electric lines of force here, E1. Similarly, this is also a positively charged plate, and because of this plate electric field here will be uh, again in this direction. So positive charge always emits electric lines of force away from itself. Is this clear? This is E1 means electric field due to this sheet, and this is E2 means electric field due to sheet 2. Is this clear to you? Tell me. Is this clear? Okay. Now in region 2 the electric field due to this sheet will be like this, E1, and electric field due to this sheet will be like this, E2. So they are oppositely directed. E1 is in this direction, E2 is in this direction.
Why are they going towards each other? Aren't they supposed to repel it?
Huh? No, they are not going to repel.
Why does it?
Actually, this is a positively charged plate. So positively charged plate will emit electric lines of force in this direction, and this is also a positively charged plate. This will also emit electric line of force here. So always the positive charge emits electric lines of force away from itself, and there is a sufficient gap between these two positive charge plates so that they are not repelling each other. There exists a repelling force, but they are actually not pushing each other because they are at a considerable good distance. Understand? Is this clear? This E1 and E2? In the same way, in region third, what is the impact of this sheet? This sheet emits electric line of force like this, E1, and similarly, this sheet also emits electric lines of force in this direction. So E1 and E2 in region third, E1 and E2 will be like this. All right. Now, on to page number 53. I am on page number 53. Behind this figure, what is written? As shown in figure, consider two thin plane parallel sheets of charge having uniform charge densities sigma 1 and sigma 2. Suppose r cap is a unit vector pointing from left to right. So we have considered that r cap is a unit vector which is pointing from left to right. So r cap is a unit vector which is pointing from left to right. I have considered it r cap. Now, region first. Let's talk about region first. This one, region first. Region first. Fields due to the two sheets are fields due to the two sheets are first of all E1 vector, and in the last class we have studied that due to a plane sheet of charge, electric field is sigma upon 2 epsilon naught. Electric field is sigma upon 2 epsilon naught. So because of this sheet, E1 will be sigma 1 upon 2 epsilon naught. So E1 will be sigma 1 upon 2 epsilon naught. But what will be the direction? As we have considered that r cap is a unit vector from left to right. So E1 is having a direction right to left. So we will put a negative sign here. Minus sigma 1 upon 2 epsilon naught r cap. In the same way, E2 vector will be E2 vector. What is the surface charge density? Sigma. So sigma 2 upon 2 epsilon naught. Sigma 2 upon 2 epsilon naught r cap, but it is also pointing in the left direction, so it is minus sigma 2 upon 2 epsilon naught. Is this clear to you, E1 and E2? And I have mentioned in the notes also negative sign because r cap is from left to right and direction of E1 and E2 is from right to left. By superposition principle, total electric field in region first is. Superposition principle means we will add up all the electric fields. So by superposition principle, total electric field in region first is E first vector, region first, E first vector is equal to E1 vector plus E2 vector. What is E1 vector? It is minus sigma 1 upon 2 epsilon naught r cap plus minus sigma 2 upon 2 epsilon naught r cap. Now, let us take minus 1 upon 2 epsilon naught E first vector is equal to minus 1 upon 2 epsilon naught sigma 1 plus sigma 2 r cap. I have taken r cap common and I have written it after the bracket, and I have taken minus 1 upon 2 epsilon naught common and I have written it before the bracket. So this is the total electric field, the net electric field in region first. Similarly, let's move on to page number 54, region second. Fields due to the two sheets are region second. Region second, fields due to the two sheets are due to the two sheets are even vector, even vector. So even vector in region second, the direction of even is from left to right. So even vector will be sigma 1 upon 2 epsilon naught, sigma 1 upon 2 epsilon naught r cap, and E2 vector is minus sigma 2 upon 2 epsilon naught r cap. Why? Because E2 is in the left direction. So left direction means negative sign. And total field, total field E second vector is equal to E1 vector plus E2 vector. So E second vector is equal to, what is E1 vector? Sigma 1 upon 2 epsilon naught r cap minus sigma 2 upon 2 epsilon naught r cap. Now take 1 upon 2 epsilon naught as common. It will be sigma 1 minus sigma 2, and take r cap common and write it after the bracket. So this is total electric field in region second. Next, region third. Region third. Fields due to the two sheets are fields due to the two sheets are even vector. Now in region third it can be clearly seen that in region third both the electric fields are in the rightward direction, and rightward direction is taken to be positive. So even vector is equal to sigma 1 upon 2 epsilon naught r cap. E2 vector is sigma 2 upon 2 epsilon naught r cap. So total field in region third will be, have you noted down this?
I'm writing, sir.
Okay. Done?
Yes, certain.
Okay. Now total field in region third is total field in region third is E third is equal to E1 vector plus E2 vector. E1 vector is sigma 1 upon 2 epsilon naught r cap. E2 vector is sigma 2 upon 2 epsilon naught r cap. Now let's take 1 upon 2 epsilon naught common and write it onto the left of the bracket. In the bracket there will be sigma 1 plus sigma 2 and r cap onto the right of the bracket. Alright. Now this was the fourth application of Gauss law. Three applications we have done in the last class. This was the fourth application of Gauss law. Now the fifth application of Gauss law is mm, we are we are on to page number 54, 54, downside of page number 54. So fifth application, electric field of two oppositely charged plane parallel plates. Electric field of two oppositely charged electric field of two oppositely charged plane parallel plates. Plane parallel plates. So now let us draw two oppositely charged plane parallel plates. Like we have drawn two similarly charged, we have drawn two positively charged plane plates which are placed parallel to each other. In the similar way, now we are going to calculate electric field due to two oppositely charged plane parallel plates. So first plate is like this. Second plate will be like this. So they are two parallel plates. So consider that it is positively charged plus, and this is negatively charged. So one plate is positively charged and another plate is negatively charged. All right. Now again in this case also there will be, let us divide the total area into three regions. So region first, region second and region third. So let us divide this entire area into three regions, region first, second and third. Now consider that this is positively charged plate. Consider that the surface charge density is plus sigma and the surface charge density of this is minus sigma. Now this is sheet 1. This is sheet 2, sheet 1, sheet 2, and R cap is from left to right, as we have taken in the earlier case also. R cap means direction. We have taken the direction left to right to be positive direction. All right. Then uh, because of this positive plate, the electric field will be electric, always positive charge emits out electric field lines. So electric field due to this positive plate will be like this, E1 vector, like this, leftwards, because it emits out. And electric field due to this negative plates, electric field lines always go inside the negative plates. So E2 vector will be like this. So E1 vector is leftwards and E2 vector is rightwards. In the same way, if we are talking about this region second, then this positive plate emits out electric fields. So E1 vector is from left to right, and this negative plate attracts electric lines of force. So electric lines of force E2 vector comes inside this negative plate, E2 vector. Is this clear to you? Are you able to see it properly? This is E1 vector and this is E2 vector. Huh? Tell me.
Yeah.
Okay. Then in region third, this positive plate emits out electric field. So E1 vector is in the right direction and this negative plate attracts electric field. So E2 vector is inside this plate. Now, as shown in figure, I am onto the last line of page number 54. As shown in figure, consider two thin parallel sheets having uniform surface charge densities plus minus sigma. Suppose R vector is a unit vector pointing from left to right. So we are supposing that R vector is a unit vector pointing from left to right. Region first. Region first. Fields due to the two sheets are fields due to the two sheets. Fields due to the two sheets are E1 vector. E1 is towards left. So E1 vector is minus sigma upon 2 epsilon naught r cap because it is towards left. That's why it is minus sigma upon 2 epsilon naught, because it is towards the left. That's why I have taken this negative sign. And E2 vector is towards right. So sigma upon 2 epsilon naught r cap. So total field region first, total field will be E first will be equal to E1 vector plus E2 vector. What is E1 vector? Minus sigma upon 2 epsilon naught r cap. What is E2 vector? Plus sigma upon 2 epsilon naught r cap. It gets cancelled because both the terms are same, but this term is with a positive sign and this term is with a negative sign. So this is 0. It is 0. So E first is equal to 0. So electric field in region first will be equal to 0. There will not be any electric field. Now region second. Region second, fields due to the two sheets are fields due to the two sheets are E1 vector is equal to now the direction of both the fields in region second. Region second means the region which is in between the two plates. So E1 vector is also from left to right and E2 vector is also from left to right. So E1 vector is equal to sigma 1 upon 2 epsilon naught r cap, and E2 vector is also left to right, so it will also be positive. This is not sigma 1 actually. So we have taken both the surface charge densities of both the plates to be the same. So sigma upon 2 epsilon naught r cap and E2 vector is equal to sigma upon 2 epsilon naught r cap. So total field in region second, sorry. Total field E second vector is equal to E1 vector plus E2 vector. E1 vector is sigma upon 2 epsilon naught r cap. E2 vector is also the same, sigma upon 2 epsilon naught r cap. So this is 2 sigma upon, after adding it will become 2 sigma upon 2 epsilon naught r cap. 2 will cancel out to sigma upon epsilon naught r cap. Okay. Is this clear to you? Region second, tell me.
Yes.
Similarly, in region third, fields due to the two sheets are fields due to the two sheets in region third, fields due to the two sheets are first of all E1 vector. So field is towards the right. So E1 vector is equal to sigma upon 2 epsilon naught r cap, and E2 vector, it is towards the left. It is towards the left. So leftward means negative. So minus sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught r cap. So what will be the total field? Total field is E third, electric field of third region. E third is equal to E1 vector plus E2 vector. E1 vector plus E2 vector. What is this E1 vector? It is sigma upon 2 epsilon naught r cap plus minus sigma. So it is not required to write plus minus. Plus minus will become minus. Minus sigma upon 2 epsilon naught r cap. So it will cancel out. It will become 0. So electric field in the third region will be 0. Is this clear? Is this clear, Anusha?
Yes, sir.
Okay. Okay, Anusha, give me 2 minutes. I am coming back. You just write down this. Okay, Anusha, have you noted down everything?
Yes, sir.
Okay, let's move on to the next slide. The last topic of this chapter, electric field due to a uniformly charged thin spherical shell. Electric field, electric field due to a uniformly charged thin spherical shell. Uniformly charged thin spherical shell. Electric field due to a uniformly charged thin spherical shell. Thin spherical shell. What is the meaning of this thin spherical shell? Actually, sphere is a ball, and if we call it ball, then it could be a solid ball also. But we are calling it a thin spherical shell. Shell means that it is hollow from inside. It means that there is only air inside that spherical ball. So let's draw it. So in the name of sphere, we draw a normal circle only. So this is a thin spherical shell. This is a thin spherical shell. So I have drawn it double circle. I have drawn a double circle because I just want to show that this spherical shell is having a small thickness also. Now now we will draw a Gaussian surface also. We will draw a Gaussian surface after outside this spherical shell. So Gaussian surface we can consider any type of. We can consider any type. We can draw any shape as a Gaussian surface. So I have drawn this the I have drawn it like a Gaussian surface, and electric field due to a uniformly charged thin spherical shell. So I'm reading out the theory of this part. Consider a thin spherical shell of radius capital R with surface charge density sigma. So I am considering a thin spherical shell, its radius is capital R. Its radius is capital R. Okay. Consider a thin spherical shell of radius capital R with surface charge density sigma. To determine electric field at any point capital P at a distance small r from O, let us consider a spherical Gaussian surface as shown in figure. So I want to calculate like in the earlier example, we have divided the entire region into three different regions. One region is onto the left of this plate, one region is between these two plates, and one region is onto the right of the this plate, right of this plate. Similarly, in the case of thin spherical shell also, we are dividing this area into three different parts. We are dividing the point, we are dividing the location of the point. Location of the point could be at any of the 3 points, at any of the 3 points. The point P where I want to calculate the electric field, it could be inside this spherical shell, it could lie on this spherical shell, or it could be outside the spherical shell. So we will consider here also, we will consider three cases. First case, when point P lies outside the spherical shell. When point P, and what is point P? Always understand that a point where we want to calculate the electric field is taken to be point P. So A part is when point P lies outside the spherical shell. When point P lies outside the spherical shell. When point P lies outside the spherical shell. Okay, flux through the Gaussian surface. Flux through the Gaussian surface phi E is equal to flux through the Gaussian surface phi E is equal to E into 4 pi r square. Alright, so when point P lies outside the spherical surface, so I have considered that point P is lying here on the Gaussian surface. So all the charge, whenever we consider that charge is distributed on this spherical shell, then there is a rule that all the charge is supposed to be concentrated at the center of this spherical shell. All the charge is supposed to be concentrated at the center of mass of any object. So I am considering this spherical shell, so all the charge is concentrated at the center of this spherical shell. So this is point P in the first case, and the distance between center O and point P is small r. Okay, and we know that what is electric flux? Electric flux is electric field. Electric flux is phi E. Electric flux is electric field into area, surface area. And what is the surface area of a Gaussian surface? Sphere. Surface area of a sphere. Surface area of a sphere is 4 pi r square. So E into 4 pi r square. By Gauss theorem, phi E is equal to Q upon epsilon naught. Q upon epsilon naught. ये हो गया phi E is equal to E into 4 pi r square, and this one is phi E is equal to Q upon epsilon naught. So there are two equations, and both the equations are giving us the value of electric flux. So comparing equation 1 and 2, I will write from first and second. From first and second, E into 4 pi r square is equal to Q upon epsilon naught. So E is equal to 1 upon 4 pi epsilon naught Q upon r square. 4 pi will come here, 1 upon 4 pi epsilon naught Q upon r square. Okay, and vectorically, E vector is equal to 1 upon 4 pi epsilon naught Q upon r square r cap. R cap is a direction. R cap is a direction outward. It is radially outwards from this sphere. Okay, because we know that if we are talking about any charge, if we are talking about that charge is distributed uniformly on this sphere, on this spherical shell, then we take that charge to be positive charge, and positive charge always radiates out electric field. So electric field will be outwards. Outward means a direction of r cap will be like this. Okay, is this clear till now? Anusha, is this clear?
Yes, sir.
Okay. Now, B part is when point P lies on the spherical shell. Lies on the When point P lies on the spherical shell. The total charge on the shell of radius r is when point P lies on the spherical shell. When point P lies here, then what is the distance between center and this point? It will be now r only. So the total charge, now I am on to page number 57. The total charge on the shell of radius r is the total charge on the shell of radius r is q is equal to sigma a. Q is equal to sigma a. I know that q is equal to sigma a. Sigma is equal to charge per unit area because it is surface charge density. So q can be written as q is equal to sigma a. Q is equal to sigma into 4 pi r square. Sigma into 4 pi r square. Equation number 1 by Gauss theorem. By Gauss theorem, phi e is equal to q upon epsilon naught. And what is phi e? Phi e will be e into 4 pi r square, and q is equal to sigma into 4 pi r square upon epsilon naught. So 4 pi r square will cancel out. I think this is clear to you, because when we have taken point P outside, then the distance, then the radius will be considered as 4 pi small r square. Now, when point P lies on the surface of this sphere, then radius will be capital R. So electric field into area of the sphere is 4 pi capital R square. So this is 4 pi r square, and here also it is 4 pi r square. So I have cancelled 4 pi r square by 4 pi r square. So E is equal to sigma upon epsilon naught. Okay. Now point C, when point P lies inside the spherical shell. Please note down till here, then I will switch on to the next slide. And please tell me whenever you complete it. Anusha? Anusha, are you there?
Yes,
Okay, okay. Are you completing
yes,
it?
no.
Okay, okay, okay.
Yeah, I'm writing one.
Okay, okay.
Yeah, I'm done.
Okay. Now, last is when point P lies inside the spherical shell. when point P lies inside the spherical shell. Lies inside the spherical shell. Now, this is the center of this spherical shell, and now point P lies inside the spherical shell. Point P is here. So the distance will be like this. This is a small r. And now considering this to be the radius, let us draw a Gaussian surface inside the sphere. Alright. As shown in figure, the charge enclosed by the Gaussian surface is 0. I know that all the charge is distributed over the surface. All the charge is distributed over the surface of that sphere. So for calculating electric field, we consider that all the charge is supposed to be concentrated at the center, but all the charge is not at the center. All the charge is located uniformly on the surface of the sphere. So what is the charge enclosed? Charge enclosed means charge which is inside. Charge enclosed is 0. Charge enclosed is 0. Charge enclosed by the sphere is equal to 0. Charge enclosed by the sphere is equal to 0. That is Q is equal to 0. Q is equal to 0. Equation number 1. Now, flux through the Gaussian surface phi E is equal to flux phi E is equal to electric field into area, E into 4 pi r square. By Gauss theorem, phi E is equal to Q upon epsilon naught, and this time the charge enclosed, because we are inside the spherical shell, the charge enclosed is 0. So this time it will be 0. 0 upon epsilon naught means 0. Alright, this is equation number 2 and this is equation number 3. Comparing second and third, from second and third equation, E into 4 pi r square is equal to 0. It implies that E is equal to 0. So electric field inside a spherical shell is always 0. Is this clear to you?